Yeah, my name is Haarika Manda, and today I'm going to be talking about our paper called TurboTest, Learning When Less is Enough Through the Early Termination of Internet Speed Tests. So let's get started, shall we? So currently, billions of the people around the world, including people in underdeveloped nations, actually lack access to high-quality internet connections. This is extremely problematic considering the internet is increasingly required for day-to-day activities, such as applying for job applications or doing different medical applications. Furthermore, even if we want to measure the quality of an internet connection, we need a lot of this information in order to actually gauge where we should build new infrastructure for people. This has led to the boom in actually measuring broadband quality, with a lot of platforms springing up, such as M-Lab, Ookla, and Cloudflare, which all allow users to run user-initiated, client-driven speed tests in order to actually get the quality of service, that is the download speed and the upload speed. However, as we all know, just because a tool is used a lot doesn't mean that there aren't any problems with it. Namely, speed tests actually impose growing costs at scale when we try and actually increase the number of tests we're running. What does that mean? Well, speed tests are extremely expensive, as more and more users are transferring to gigabit Ethernet connections, as I'm showing you through this left diagram on the left. Our download speeds are actually increasing, and platforms have to transfer more and more packets in order to actually measure people's data. The measurement platform M-Lab reported that there was a 23 times increase in the amount of data that we dealt with, all the way to up to 12 petabytes year over year. Given its expensiveness, it's actually hard to scale a lot of this infrastructure. And this led to the situation where a lot of speed test data is actually redundant. And we want to answer the question, do we actually need to run a static 10+ second speed test, or are there some types of connections that we can terminate early? In order to answer this question, we actually need to understand the natural distribution of speed tests. That is, what types of speed tests are most problematic and actually contribute to a lot of the data transfer costs. In order to do this, we looked at 1 million download tests from 2024 to 2025, and we grouped these download tests based on our speed tier. As we can see from this diagram, low throughput speed tests account for the majority of tests that are run in terms of absolute volume. But when we start to look at the amount of data transferred, we see that these axes are flipped, and a small percentage of speed tests, that is high throughput, majorly gigabit Ethernet connections, are actually contributing to around 50% of the data transferred. So can we actually try to reduce the amount of data transferred by a lot of these problematic speed tests? And can we try and send fewer packets and probes while still reporting the same type of accuracy or download speed and upload speed? So this is what we aim to answer. So let's look at this example of a typical speed test run by a user. Essentially, we have the user who sits at home and is trying to run a speed test. And then we have a speed test server where it's trying to essentially send download packets to the client in order to report our final download speed, or X Mbps. So let's try and apply some existing heuristic-based strategies in order to see if they can actually terminate the speed test early, report the throughput, without actually sacrificing our accuracy. Let's try and apply an existing heuristic that was published in SIGCOMP-CCR last year. This type of heuristic tried to leverage the inherent congestion control signal, that is BBR, that's used in speed tests. BBR essentially tries to ramp up and increase our congestion window size. Let's try and apply this heuristic and see if we can terminate early. In this example speed test, however, unfortunately, even though our ground truth output is 687 Mbps, when we apply this heuristic that tries to terminate early, it has an extremely high relative error of 42% and is off by 200 Mbps. So what's happening? It's actually that this BBR heuristic is failing to balance the trade-off between data savings and accuracy. It's actually terminating early, unfortunately. And this shows that there's not exactly a direct correlation between congestion control and throughput stability. So how can we improve upon this? And can we try and reevaluate our ground truth statement of what it means to terminate a speed test early? So let's try and reframe this. Essentially, we want to terminate a speed test early by predicting a value close to our ground truth by balancing two optimization variables. We want low prediction error, number one, and we also want low data transfer. Given that we need to optimize two variables, doesn't it make sense to decompose this into two learning strategies? This is what a lot of these heuristics fail to do. Let's see if we can do this by leveraging ML. Namely, we can take our speed test time series statistics and actually aim to optimize our first variable, that is prediction error, using a regressor module. However, since we still need to actually optimize data transfer, we can actually have our second stage, that is the termination stage, that deals with actually finding the ideal stopping point and actually saving the data. However, I know that this is a lot to take in all at once, so let's try and break this down step by step and look at our first stage. That is, how exactly do we predict our final throughput? So as input, for example, we're taking the speed test time series statistics. But what does that actually mean? Well, this is just the kernel level TCP info information that you're getting at the server side when an ISP or an operator is initiating a speed test. This includes like throughput samples, congestion window size, as well as retransmissions. These are all variables that kind of indicate the burstiness or stability of a connection. We essentially want to give these variables to our model to give an intuition about the type of connection that is ongoing. So let's try and look at an example where we're kind of inputting these types of variables. In our example, our ground truth is 50 Mbps, and we're trying to input all these time series statistics to our regressor model that's trying to minimize prediction error. So what happens when we apply this model at every time step? Well, we get an output sort of like this, where initially, at our initial time steps, our model doesn't have enough information to actually predict close to our ground truth, where we're off by a lot. If, for example, we're predicting 25 Mbps initially. However, as we're going towards the end of the speed test, we have a more accurate prediction. However, that's at the cost of data savings. So in this case, even though we have low prediction error, like high prediction error, our data savings is extremely high. But the reverse in the case over here, where we're ending really late, so we have a really accurate prediction, but our data savings is low. So initially, we can't exactly give this model to an operator by itself because we're not exactly balancing accuracy versus data savings. Namely, we still need to answer our second question. That is, given our final throughput, where should we actually stop, and when is the optimal stopping point? We also need to make sure that this is tunable from an operator perspective to see if they actually prioritize data savings or accuracy. So this is where our second stage comes in, where we actually learn where to stop, essentially. This classifier-based model essentially allows us to give an operator tunable tolerance threshold called epsilon. Namely, what does this mean? Well, at epsilon equal to 5%, that means the operator is only tolerating an error, which is really low, equal to 5%. However, as an operator, if I want more data savings, I can say I can tolerate more error as long as I have more data savings. So let's go back to our previous example of 50 Mbps, and let's try applying an epsilon of 15 or 15%. So we can translate all of these absolute values in terms of percentages. And as we can see, initially, as I said before, our error or relative error tolerance is pretty high. And as we go towards the end, our relative error is pretty low. So given that epsilon is equal to 15, as we can see intuitively, it's actually available that our ideal stopping point is 4 seconds. Essentially, using this labeling-based strategy, we can teach our classifier model to stop at our ideal stopping point given an epsilon. And so we can essentially train individual epsilon-based models depending on what the operator wants. So now that we can actually optimize for low prediction error and low data transfer, how do we exactly put this together, given that we have our transformer-based classifier that actually can learn the earliest point where we have an operator-specified tolerance? This is where we put the two stages together and we get our TurboTest-based framework. We kind of train our model on the 800K real-world speed test from M-Lab and try and come up with the inference-based workflow that I'm showing here. The key point, however, is we don't want to apply the regressor at each time step, so we kind of reverse our workflow where we're applying our termination-based classifier initially, and it predicts our final ideal stopping point. So we only have to apply our regressor once at the end, and then it's giving us our X Mbps. So we're only applying the regressor whenever our classifier is essentially suggesting significant confidence in our termination decision. So now that we have this framework, we want to see if it actually works as our intuition is showing us. Namely, does it actually extend the accuracy savings frontier? In order to do this, we actually have our two similar metrics of success that I was showing earlier. We have we want to make sure that we have low cumulative data transferred after summing up the data that's actually transferred when applying TurboTest on our sampled 1 million test data set. We also want to make sure our median relative error over this entire entire data set is extremely low. So we can essentially plot our two metrics for success on our x-axis and y-axis, where our x-axis indicates our relative error and our y-axis indicates our data transfer. And namely, our ideal solution will be right here at the top right. So what happens if we apply TurboTest as well as BBR in some other heuristics-based solutions? Where do they stand on this plot? So as you can see, when I apply TurboTest, BBR, and CIS, another heuristic, we see that TurboTest is all the way at the top, which indicates that it transfers the least amount of data out of all three solutions. And when we look at the other metric of relative error, we can see that at every point in which we have the same data transferred, it actually has the same or less relative error. So let me take a 20% relative error, for example. When I draw this line, we can see that the TurboTest-based method transfers 2 to 4 times less data than BBR while achieving a same prediction accuracy. So what does this mean in terms of real-world data savings, right? Let's look at the 12 petabytes example that I was showing to you earlier. So when we applied the epsilon equal to 15 model of TurboTest on M-Lab's data for 1 month, what happens is if we actually reduce M-Lab's monthly overhead from 12 petabytes of packet traffic all the way to one petabyte. So this massively decreases the amount of infrastructure costs as well as the amount of costs when it comes to running millions of speed tests every day. But now that we applied TurboTest on our general use case, we actually need to see how does TurboTest actually perform in our key high throughput and gigabit Ethernet speed tests that I was talking to you about earlier. Namely, which types of niche tests actually benefit the most from TurboTest. To build intuition on this, if you remember when I showed you the data volume transferred earlier, we saw that high throughput tests essentially contributed to a lot of the raw data volume transferred, even though they were only a small percentage of the tests. So let's break down our results based on throughput and RTT to see how essentially TurboTest and its next best heuristic BBR stack up. So we have our x-axis over here, which shows us the RTT bin, and our y-axis that shows us all the stages of our speed tier. And we try and plot up our point sizes as bubbles, which indicate the magnitude of difference in which TurboTest does better or BBR does better. We see over here, amazingly, that in a lot of our cases, that TurboTest does much better in green. And even when we try and focus on the key high throughput speed tests, which are the most problematic for these operators, TurboTest is actually able to outperform BBR massively, as indicated by the proportional sizes of these bubbles. This shows that TurboTest's largest gains are in high throughput tests, the same conditions where BBR struggles the most. So what are our takeaways from this? Well, the main takeaways are that we were able to showcase the limitations of existing static speed tests and heuristic-based approaches. We were able to show that BBR actually balances 2 parameters, and it's able to optimize both accuracy and data transferred by using machine learning, and it optimizes and outperforms BBR by 1.8 to 4.4 times in terms of data transferred. We saw that in our sample data set of 1 million randomly sampled real-world speed tests, TurboTest is actually able to leverage the temporal patterns inherent in speed tests to outperform prior methods keyly on these problematic high-throughput gigabit tests. And finally, we actually make TurboTest efficient and deployable by exposing a tunable parameter that allows the operator to essentially tune how accurate or how long it takes it to stop. So thank you for listening to my talk, and you can reach out to me. I'm Haarika Manda at hmanda@ucsp.edu, and you can find all the details of the paper where we kind of go into more details of the evaluation strategy and how to tune TurboTest. Thank you.